oxidation-reduction reactions. The single displacement reaction between metallic magnesium and an aqueous solution of copper-2 sulfate will be used to introduce the concepts of oxidation and reduction. According to the chemical equation shown, magnesium is reacting with a solution of copper-2 sulfate where copper gets displaced and a solution of magnesium sulfate is produced. Formulating the ionic equation from this, we get magnesium, copper-2 ions, sulfate ions, magnesium ions, sulfate ions, and copper atoms. Be reminded that elements and molecules are not decomposed when formulating ionic equations. Removing the spectator ions, which in this case are sulfate ions, we end up with the net ionic equation. According to the net ionic equation, we're having a magnesium atom reacting with a copper-2 ion to give you a magnesium ion and a copper atom. Many theories have been used to explain redox changes, but the one that is used in this tutorial is called the electron transfer theory. According to the electron transfer theory, the magnesium atom, being more electropositive than copper, forces 2 electrons onto a copper-2 ion. Or we can say that the copper-2 ion, being a stronger oxidizing agent than a magnesium atom, takes 2 electrons away from it. As a result of this, the magnesium atom is changed into a magnesium ion, which is now soluble in water, and a copper-2 ion is changed into a copper atom, which now becomes insoluble in water and thus precipitates out of solution. Oxidation is defined as the loss of electrons, while reduction is defined as the gain of electrons. This equation depicts how a magnesium atom gets oxidized into a magnesium ion by losing 2 electrons, and how a copper-2 ion accepts the 2 electrons produced by the magnesium ion and gets reduced into a copper atom. These 2 figures depict this chemical change. In this figure, we are seeing how a strip of magnesium is immersed into a blue solution of copper-2 sulfate. And as the reaction proceeds, copper-2 ions are replaced by magnesium ions. As a result of that, the blue solutions turn colorless since magnesium ions are colorless. Also, we can see that a deposit of copper is being formed at the bottom here since it gets displaced by magnesium. This net ionic equation can be resolved into its 2-half equation. The first half equation represents the oxidation of magnesium, and the second one exemplifies the reduction of copper-2 ions into copper. This first half equation represents oxidation, and the second half equation represents reduction. This is a summary of what we've done there, and we have introduced the concepts of reducing and oxidizing agents. Magnesium loses 2 electrons and gets oxidized to a magnesium ion. In this case, the copper-2 ion is acting as the oxidizing agent or the electron acceptor. In the second half equation, copper-2 ion accepts 2 electrons and gets reduced into a copper atom. In this case, the magnesium atom is acting as the reducing agent, or what is called the electron donor. Of course, we are not talking about 1 atom and 1 ion. A series of that happens, okay? So over a time, the entire solution here is going to get colorless. To further consolidate our understanding of redox changes, we'll do another example of a single displacement reaction. Only in this case, copper is reacting with a solution of silver nitrate to produce copper-2 nitrate with silver being precipitated out of solution. Writing the net ionic equation for the reaction, we end up with this one as shown here. Nitrate ions are common on both sides of the equation, so removing these spectator ions, we are now left with the net ionic equation as shown here. Again, Using the electron transfer theory, we say that in this case, copper being more electropositive than silver forces 2 electrons onto 2 silver ions, or we can say that silver ions, being stronger oxidizing agents than a copper atom, take 2 electrons from it, and as a result of this, the copper atom is changed into a copper 2 ion, which is soluble in water, and the 2 silver ions are changed into 2 silver atoms, which now become insoluble in water and thus precipitate out of solution. And these two figures try to depict that chemical change. In this first one, we are having a colorless solution of silver nitrate with a strip of copper inserted into it. After the reaction has taken place, we can see that a blue solution of copper nitrate is formed and silver is being deposited as a solid. This equation shows how the reduction and oxidation happens. Here we have seen how a copper atom gets oxidized into a copper ion by losing 2 electrons. The 2 electrons that are produced in this process get accepted by 2 silver ions, which get deposited as silver atoms. Writing the 2-half equation for that redox change, we have copper atoms being changed into copper ions with a production of electrons, so that represents oxidation. And in the other half equation or reaction, we are seeing how silver ions are accepting electrons to form silver atoms, and that represents reduction. In this case, let's see what are the reducing agents and the oxidizing agents. Each copper atom loses 2 electrons and gets oxidized into a copper ion. In this case, the silver ions are acting as the oxidizing agent or the electron acceptor. 2 silver ions accept 2 electrons and get reduced to 2 silver atoms. In this case, the copper atom is acting as the reducing agent, or what is called the electron donor. In these reactions, reduction as well as oxidation happens simultaneously. As such, they're called redox reactions. Oxidation states and oxidation numbers. Iron forms 2 oxides when it reacts with oxygen, iron 2 oxide and iron 3 oxide. These 2 compounds are used to introduce the concepts of oxidation numbers and oxidation states. However, before these can be achieved, we need to heed the following guidelines. In all neutral compounds, the sum of the oxidation numbers for all elements present must be 0. Since the oxidation numbers for some species are known, it facilitates the determination of those that are unknown. The following are guidelines to knowing the oxidation numbers for some ions and atoms. All ions of atoms with standard valencies will have oxidation numbers that correspond to the valence on the ions. For example, Ca2+ will have an oxidation number of +2. And that of bromine 1 negative will be negative. The atoms of all elements will have oxidation numbers of 0. Examples of these are any element in the atomic form or the molecular form. Hydrogen in all compounds will have an oxidation number of +1, except in hydrides where it is -1. For examples, in hydrogen chlorate, hydrogen is +1, and in potassium hydride, the oxidation number of hydrogen is -1. Oxygen in all compounds will have an oxidation number of -2, except in peroxides where it is -1. For examples, in sulfuric acid, the oxidation number of oxygen is -2, but in hydrogen peroxide, it is -1. Now we shall use these guidelines to find the oxidation numbers of iron in iron 2 oxide and in iron 3 oxide, and to speak about their relative oxidation states. Since iron is a neutral compound, the sum of the oxidation numbers on the iron ion and the oxygen ion must be 0. Since we know the oxidation number of oxygen is negative 2, then the oxidation number of iron must be positive 2 for the sum to be 0. Neutral compound, this is negative 2. For that to be 0, this must be positive 2. Since iron 3 oxide is a neutral compound, the sum of the oxidation numbers on the iron ion and the oxygen ion must be 0. Since we do not know that for iron, let it be represented by X. In this compound, we are having 3 oxygen atoms and 2 iron atoms. We know the oxidation number for oxygen is negative 2, so doing the math here, we'll end up with negative 6 plus 2x is equal to 0. Therefore, 2x must be equal to positive 6 when you take across the negative 6 that side, and x must be positive 3. So the oxidation number for iron in iron 3 is equal to a positive 3. Now we compare the oxidation states of iron in these two compounds. According to the number line presented here, the less negative a species is, the greater is its oxidation state. So if something had an oxidation number of negative 6, and then after a redox change, it acquired an oxidation number of negative 2, we will say that when it has an oxidation number of negative 2, it is at a higher oxidation state than when it had an oxidation number of negative 6. So in this case, because iron in iron 2 oxide had an oxidation number of positive 2, and in iron 3 oxide, it had an oxidation number of positive 3, we say that in iron 3 oxide, the iron was at a higher oxidation state. This equation shows how iron has acquired a higher oxidation state when iron 2 gets oxidized into iron 3 by losing an electron. Now we shall do some other examples to consolidate your understanding of how to determine the oxidation number of any species that is unknown. The first example is finding the oxidation number of nitrogen in the compound nitrogen monoxide. Being a neutral compound, the sum of the oxidation numbers of the elements present in it must be 0. But we know that the oxidation number of oxygen is negative 2, so we let X represent that for nitrogen and solve for it. So it has 1 oxygen and 1 nitrogen. We know that the oxygen is negative 2, therefore X plus negative 2 must be equal to 0, and X must be equal to positive 2. So the oxidation number of nitrogen in this molecule here is positive 2. Let us see what it is for nitrogen in nitrogen dioxide. Again, we know it is a neutral compound. As such, the oxidation numbers for all the species present must be equal to 0. We know that oxygen is negative 2, so allow X to represent that for nitrogen. However, in this case, we are having 1 nitrogen and 2 oxygens. So X minus 4 is equal to 0. Therefore, X must be equal to positive 4. The oxidation number of nitrogen in NO2 is thus positive 4. So comparing the oxidation numbers of nitrogen in those two different compounds, we see that nitrogen here is having an oxidation number of positive 2, and this one here is positive 4. Therefore, we say that in nitrogen dioxide, the nitrogen is at a higher oxidation state than the nitrogen in nitrogen monoxide. Why is that so? Because we are having an extra oxygen, and oxygen has a higher affinity for electrons. As such, it will pull more electrons away from the nitrogen atom, making it become more positive. Returning to our number line, they show that the nitrogen in NO2 with an oxidation number of positive 4 is at a higher oxidation state than this nitrogen in the NO molecule. Next, we're given a series of compounds in which carbon is present, and we are asked to find the oxidation numbers for the carbon in these various compounds. The first one is methane. Of course, we know it's a neutral compound. We know what hydrogen is. Let X be that for carbon, and we solve for it. You have 1 carbon and 4 hydrogen, 1 carbon, 4 hydrogen, X plus 4 equal to 0, X is equal to negative 4. So the oxidation number for carbon in methane is negative 4. Next, for carbon in hydrogen carbonate. Again, this is a neutral compound. We know what hydrogen is. We know what oxygen is. We can let X be that for carbon and we solve for it. So we have 2 hydrogens, 1 carbon, 3 oxygens. That's X for carbon. 2 times that is positive 2. 3 times that negative 6. Do the math. This works out to be negative 4 plus X is equal to 0. X is equal to positive 4. So the oxidation number of carbon in this molecule here is positive 4. In methane, it was negative 4, and in this molecule here, it is changed to positive 4. So it is at a higher oxidation state than in this one here. We must now define the oxidation number for sulfur in sodium thiosulfate. Again, it's a neutral compound. We know this with standard valence. We know that. Let X be that for sulfur. And solve for it. We're having 2 sodium, 2 sulfurs, 3 oxygen. We know what sodium is, positive 1. That's going to be 2X here. And that's going to be 3 times negative 2. Doing the math, we end up with positive 2 plus 2X minus 6 is equal to 0. So X minus 4 is equal to 0. 2X is equal to 4. Therefore, X must be equal to a positive 2. So the oxidation number of sulfur inside here is positive 2. Now we come to finding the oxidation number of a species in an ion. And in this case, we're trying to find the oxidation number of chromium in this dichromate ion with a valence of 2 negative. Now it's a slightly different world game. It's not a neutral compound, but it's a compound with a valence of 2 negative. So that means that the sum of the oxidation numbers for all the species present must be equal to negative 2. Again, we allow X to be that for chromium and solve for it. So we have 2 chromiums, 7 oxygen, 2X minus 14 is equal to negative 2. Bring across that, it becomes positive 14. With that negative 2, we end up with positive 12. So X is equal to positive 6. So the oxidation number for chromium in that dichromate ion there is positive 6. And this brings us to a positively charged ion, that is ammonium ion. It's not neutral, so the sum of the oxidation numbers must be positive 1. We know that for hydrogen is positive 1. Let that for nitrogen be X and solve for it. You have 1 nitrogen, 4 hydrogen. This is X for the positive 1, and that must be equal to positive 1 since that's the valence in the ammonium ion. Then in math, we end up that the oxidation number for nitrogen in ammonia is negative 3. The following activity involves determining whether or not redox reactions happen in the equations provided. To do that, you will have to find the oxidation numbers for the various species present and look to see if there is a change in the oxidation numbers for any of the species present. This is hydrogen peroxide being decomposed into water and oxygen. We know that in peroxides, oxygen is negative 1, but in its molecular form, it is 0. So right away now you can see there's a change in oxidation number here. 2 of the oxygens get oxidized, okay, because we're removing negative and making it 0. And in this case, you can see that, again, there's a change in oxidation number for 2 of the oxygens that got reduced. Oxygen is changed from negative 1 to negative 2. Yes, this is a redox reaction. Does it happen here? Okay, we'll check. All elements will have oxidation numbers of 0, 0. But now we have to check the oxidation numbers for these here. We know what is it for silver. We know what is it for oxygen. Let X be that for nitrogen. Now, one thing is this. When you're doing oxidation numbers for the various elements present, ignore the coefficient that is present there, okay? So we have 1 silver, X, and 3 oxygen. When you do the math here, it becomes X minus 5 is equal to 0. Therefore, X is equal to positive 5. That's the oxidation number for nitrogen in the species here. Same thing applies here. Here you have 1 zinc. We know zinc is standard, positive 2. But you have a 2 outside the bracket here. So that means you have 2 nitrogens and 6 oxygens. So let that be 2x, 6 into a negative 2. Then you do the math, you end up with 2x minus 10 is equal to 0, and x is equal to positive 5. So you see that? In both cases, the oxidation number for nitrogen is the same. Is this a redox reaction? Yes. Zinc is changed from 0 to a positive 2, and silver is changed from a positive 1 to 0. Okay? That's the oxidation there, and this here is a reduction. Point to note is this, that if you have found the oxidation number for, say, nitrogen in a nitrate ion here, you don't need to find what is it for this when it is with zinc, because in all nitrates, nitrogen have the same oxidation number. The same thing goes for other nonmetals. Let us say that you have sulfur in a sulfate ion. Let us see what is it for sodium sulfate, and then we see what is it in calcium sulfate, so we can make a general rule. Okay, neutral compound, 2 sodiums, 4 oxygens, 1 sulfur. Let x be that for sulfur. So 2 plus x, 4 times negative 2, you end up with x minus 6 is equal to 0, and x is equal to positive 6. In this case, a neutral compound, calcium is 2 plus, oxygen is 2 negative. Let that be x. So you're going to have positive 2, negative 8. You end up with x minus 6 is equal to 0. X is equal to positive 6. See that? So if you found the oxidation number here, it wasn't necessary for you to go and find the oxidation number here. As long as the radical stays the same, the non-metal that is unknown will have the same oxidation number. Let's do another one. Here's sodium chloride. We want to know what chlorine is. All right? Neutral, 1 sodium, 1 chlorine, let it be x. You have 3 oxygens. So you end up with x minus 5 is equal to 0. X is equal to positive 5. Try for this one here. Watch now. You have 1 calcium, but you have 2 chlorine and 6 oxygen because of that too. So 1 calcium, 2 chlorine, 2x, and 6 oxygen, you end up with 2x minus 10 is equal to that. Again, you see, the oxidation number for the chlorine is same there and there. So if you have chlorate ions and you found the oxidation number in one compound, it stays the same in the other one. We can do it for a sulfite radical too. It's 0 sum of oxidation numbers. We have 2 sodiums, 1 sulfur, 3 oxygens. Let it be x. When you do the math, you're going to have x minus 4 is equal to 0. X is equal to positive 4. Neutral compound. You have 1 calcium, 1 sulfur, 3 oxygens. X minus 4 is equal to 0. And same thing here. Okay, so if you know the oxidation number of sulfur in one sulfite radical, no need to go find it again if it is with a different metal here. Well, thank you for listening, and I hope that was very useful to you.